We're recording. All right. Good morning, everybody. We are starting question 2015, numbers 1 and 2 today. The game plan, my goal, is to do 3 and 4 tomorrow, Friday. I know it starts spring break, but I'm going to do 4 and 5 tomorrow. And I'm actually going to do 5 and 6 on Monday. Okay, so it's just one day of spring break. I'm going to go ahead and upload all of 2016 during spring break as well. I'm going to do it as one video. Well, maybe not one video, but on one day, maybe like Tuesday or something. So you can kind of have that to look over and work on during spring break. I don't really want us to have that too much, too long off from our studies. Okay. So let's start with question 1. It says the rate at which, and I know my audio has been messing up on some of these videos. I'm going to try really hard to be conscious of that as I'm doing this today. So try to stay in the same position and talk like this. I think this should hopefully help my audio. It says the rate at which rainfall water flows into a drain pipe is modeled by the function r, where r of t is equal to the sine equation. Now this is flowing into a drain pipe, so you would call this a rate in function, right? That's a rate in function. And this is between 0 and 8 hours. And the pipe is partially blocked, allowing water to drain out of the other end of the pipe at a rate modeled by this. So this function here is a rate out function. Okay. And this is again between 0 and 8 hours. And initially there are 30 cubic feet of water in the pipe at time equals 0. Okay. So we don't have to do it yet, but I'm sure it's coming up. I got rate in, rate out, and an initial value. I can model this equation if I really want to. Like I can say, hey, the amount that we have, we've done this so many times, the amount is equivalent to my initial value 30 plus the integral of rate in minus rate out. So we'll just go ahead and write that. Initially at time equals 0, we'll say to any time t. And remember, I'm going to choose a different variable for the function. I'm going to say r of x, rate in minus rate out, which we'll say is d of x dt. Okay, so that might come up. That might be helpful later, but that's how we figure out the amount. Okay. Anyway, that is a certain type of problem that we've talked about, so it's good that it's showing up. How many cubic feet of rainwater flow into the pipe during the 8-hour time interval 0 to 8? All right. How many cubic feet flow in? So we're dealing just with our rate in function. So if I want to know how much flows in, that's simply the integral 0 to 8 of my r of t equation. And I plugged this. So at the very beginning, if this calc active, I went ahead and plugged that into y1, and I plugged my rate out function into y2. That way I never had to rewrite them. But in my calculator, all I did was the integral 0 to 8 of y1 dx, and my calculator told me it was 76.570 cubic feet. Okay, that's part A. Cool, let's move on to B. All right, B says, is the amount of water in the pipe increasing or decreasing at time equals 3? Give a reason for your answer. All right, if I want to know if the amount of water is decreasing or increasing at time equals 3, I got to look at the derivative, okay, the derivative of my amount, and decide if it's going to be positive or negative. If it's positive, it's increasing. If it's negative, it's decreasing. Okay. So, okay, we came up with the amount equation in part A. If I take the derivative of that, remember, for these rate in, rate out problems, the derivative or the rate is just equivalent to the rate in, so r of t, minus the rate out, or d of t. Okay. So basically, I'm just trying to plug 3 into both of these, and again, I have these two equations stored in my calculator. So I'm going to do r of 3 minus d of 3. Okay. And in my calculator, I did y1 of 3 minus y2 of 3. Like I had stored them into my y1 and y2 respectively. Okay. Anyway, whenever I do this, I get negative, so that's really all I need, but negative 0.313632, which that value is less than 0. Okay. So based off of that, we would say that my function is decreasing. Okay. So why is it decreasing? The rate of the amount of water, so the rate of what I'm looking at here, the rate of the amount of water in the pipe is negative at t equals 3 and therefore decreasing. Okay, so hopefully my audio is doing okay. Really praying it is, but we'll see. That was part B. It wasn't too terrible. It's just recognizing increasing, decreasing has to do with derivative, and we know the derivative is just this rate function here. Rate in minus rate out. Okay, let's move on to C. C says, at what time in the inclusive interval 0 to 8, so 0 and 8 are included, is the amount of water in the pipe at a minimum? Okay, so a minimum value, and justify your answer. So a minimum is, I'm going to say an absolute minimum in this case. I'm going to treat it like an absolute minimum, especially because we're given endpoints. Okay, so you want to check all critical points and you want to check all endpoints to determine what your absolute minimum is. Okay. So first off, let's start with figuring out our critical points. Now, critical points occur whenever the derivative is equal to 0. So I know my derivative was r of t minus d of t. And I'm trying to solve where this is equal to 0. Another way of saying that is where r of t is equal to d of t. And again, I have both those functions stored in my calculator in y1 and y2. I set my window on my calculator between 0 and 8. I might still have it actually stored. I do still have it stored. Okay, cool. So like I stored those in my calculator. You can see right there. And I graphed it between 0 and 8 and did zoom fit, so it gave me this nice clean function. Okay. So I found the intersection, and the intersection was at 0 for one of them actually, which is an endpoint, but the main one was t equals, I got, what did I get? 3.2716584. Okay, so that's my critical point. Now, to determine if it's a minimum, remember that amount function that I came up with earlier, right? The amount function I came up with earlier was 30 plus 0 to t of r of x minus d of x dx, okay? Now, if I want to know which one's a minimum between my endpoints and my critical points, I'm just going to plug all those values in for t. Into this equation, which again, you can just type this out in the calculator and determine your answer. And I put it in a little chart. So for time and amount, I plugged in 0, I plugged in 3.2716584, and I also plugged in my 8. Okay. If I plug 0 in, that's my initial amount, 30. If I plug 3.2 in, I get 27.964561. And if I plug 8 into that, I get 48.54386. Or 686, whatever. Anywho, testing all my points, it's clear to see that my absolute minimum is that 3.2. And there you have it. So we got our absolute minimum is 3.27. The justification of your answer is pretty much all that. You can maybe throw an extreme value theorem if you want to, saying we had to test the endpoints, but it's not required. It's not in the answer key. They just have a chart. So there you go. There's your justification. And then lastly, part D for number 1. D says, and I'm really surprised this is a D question because this is actually really easy. And D questions are usually hard. It says the pipe can hold 50 cubic feet of water before overflowing. Okay. For time greater than 8, water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow. Write, but do not solve, an equation involving one or more intervals that gives the time W when the pipe will begin to overflow. Okay, all it wants me to do is come up with an equation to figure out the time when the amount of water is equal to 50. Right? That's all. So when will it begin to overflow? That's when it equals 50. So I need to have some function that equals 50. But I already have an equation for amount. I found that in parts A and B. The amount is 30 plus integral 0. In this case, instead of saying t, I'm going to say w because that's the new variable, 0 to w. And then we'll say rate in, r of t, minus rate out, d of t, dt, and set that equal to 50. And that's it. I mean, this is right here is the equation of the amount. Okay, and I want to set that amount equal to 50. We're just solving for w now. So again, that one wasn't the most terrible problem in the world, but maybe I guess students overthought it or something. I don't know, but I think that was pretty straightforward. Okay. All right, cool. That was number 1, a rate in, rate out problem, and it's just a type that we may run into. So cool. Here is the answer key. So for like letter A here, we set up the correct integrand and we got the answer. Okay, I mean that was pretty simple. For letter B here, we considered R of 3 and D of 3. We considered that by setting up that equation there and an answer with a reason. They said that R of 3 was less than D of 3, but that's another way of saying like we stuck with this justification that it was a negative value. So I think both justifications are fine. C, we did set the derivative equal to 0. We found the answer, and our justification was, I would say, this entire chart. And the fact that the amount of water is least at 3.21271 or whatever. Okay. And then lastly, we set up the integral and the equation. So we had the correct integration, and we had an equation equaling 50. And again, I don't think D was too terrible. So that's rate in, rate out. Let's move on to number 2. Number 2 is a parametric. Okay, so number 2, I feel like probably won't be on your AP exam because they cut out all parametric and polars and all that stuff. But still a good problem, and honestly one that this is probably the easiest parametric problem I've ever seen because it doesn't require. It's all computational. Like, do you know this formula? Do you know this formula? Do you know this formula? So I think if you tried this on your own, I think you do pretty okay with it if you could memorize that unit. But let's try A. Okay. A says find the well, first of all, at time greater than 0 or equal to 0, a particle moving along a curve in the xy plane has a position x of t, y of t. That's a parametric with velocity vector v of t. So it's not explicitly telling you the position function. It's actually telling you the derivative. It's telling you the velocity vectors or the velocity formulas. And at time equals 1, the particle is at the point 3, 5. So we also got an initial position. Okay. So part A says find the x-coordinate only. I don't care about the y, just the x-coordinate of the position at time equals 2. Well, we're given the velocity, not the position function. So how do I work backwards from the velocity to the position? You integrate it. But remember, integration is going to tell you an accumulation. So we got to start with what we know. We got to start with the point time equals 1. and at time equals 1, I know my x value is 3. Okay? So I'm going to do 3 plus the integral of. I'm going to do my change in distance from time equals 1, which I know is 3, to time equals 2, which is what I'm looking for. And I want to find that accumulation from the x equation. Okay? So that is cosine of t squared dt. And this was calc-active. I typed that in exactly like I wrote it, and I got 2.557. And again, how this works, what this means is we take our initial x position, add the change in distance from time equals 1 to time equals 2, and I'm at my current position, 2.557. Not the craziest thing. We've seen some problems like that. All right, number 2, or I'm sorry, B. Between 0 and 1, there is a point on the curve at which the line tangent, to the curve has a slope of 2. So that means that that dy over dx equals 2. There is a tangent line whose slope is 2. That is telling us that dy over dx equals 2. I want to know what that time is that gives us that slope. So if I want to know that, I need to figure out what dy over dx is. And all you have to memorize is with parametrics, dy over dx, so dy over dx is equal to y prime divided by x prime, which we're given right here. Okay, so that's equal to e to the 0.5 t power divided by cosine of t squared. Okay, and in my calculator, I typed that into y1, and I also typed in 2 into y2. Okay, I set my windows between 0 and 1. All right, so I'm only looking at the graph between 0 and 1. And again, I plugged this as y1, this as y2. I found the intersection, and I got time equals 0.840. So yeah, not the craziest problem in the world. It's just testing your knowledge of parametrics, right? That you know all these formulas. C is not bad. Find the time at which the speed of the particle is 3. All right, well, what the heck is speed? Well, if you remember, speed is the magnitude of velocity, okay, which in parametrics is equivalent to the square root of x prime squared plus y prime squared. So this would be like cosine of t squared quantity squared plus e to the 0.5 t power squared. And I'm setting that equal to 3. I want to know when that speed is equal to 3, what time. So again, guys, all I did was plug this function into y1. I plugged this into y2. In my graphing calculator, I graphed it and worked to find the intersection, and it wasn't that terrible. T equals 2.196. Okay. And you can pause the video and try that on your own. Okay. Again, this video is all just trying to explain how it's done, and hopefully you've already kind of attempted it, but type that in the calculator. Right. And then lastly, D says find the total distance traveled by the particle from 0 to 1. Again, that's just a formula. We know that total distance is equivalent to the integral a to b of my magnitude. I guess dt. Okay, that's it. That's all it is. So we already know what this is equivalent to. We found that we set it up in C. So all we have to do is the integral 0 to 1 of what I wrote in part C. So it was the square root of cosine t squared plus e to the 0.5t quantity squared. And I'll give you a second. You can try that in the calculator, but what I got was 1.595. So, man, oh man, so far I wish we were in the year 2015 because both number 1 and 2 I think were pretty common doable problems that we've run into. Okay, and the pattern is, guys, is like I would not, so like 2019's question, I would predict not a lot of overlap would be in 2020s. I think they start to recycle every 6 or 7 years. So I'm hoping that we're going to have something like 2014 or something like 2015 in the final exam. So we will see. But man, we did that in 20 minutes, right? That wasn't terrible at all. Here's the answer key. We did the integral. Okay, so we set up the correct integral. We did the initial condition of 3, and we got the answer. We set the slope up in terms of t, so we set that up correctly. We set it equal to 2, and we got the answer. Okay, again, this is all done in the calc. We set up this speed equation. Okay, so we got that equation. And we set it equal to 3 and got the answer. And in the last one, we set up the correct integral, which was the integration of what we came up with in C from 0 to 1, and then we got the answer. So good problem, fun problem. But that does it. So good luck, and we will go on to questions 3 and 4 tomorrow, 5 and 6 Monday, and then I'll upload all of 2016 probably Tuesday. Okay. Enjoy your day.